Hello, everyone. This is Dr. White with the first in a projected set of two screencasts on section 6.3, the chi-square test for goodness of fit. So you'll need to make sure that you have the package TigerStats attached. So I want you to imagine that you are out in the wild west of the 19th century in America, and that you're the sheriff of a small town in the wild west. So maybe that person on the slides is you. And let's say a gambler comes to town, and he plays in the local saloon. He claims to play with fair dice, but the locals in the saloon, they're grumbling that he wins much too often, and they think his dice are weighted. And so they come to you, and they want you to do something about this because you're the sheriff. So you go to the gambler and you impound one of his dice, okay? And you're about to crack it open with your hammer to see if it's weighted on one side or the other. But the gambler says, no, please, don't break my die open. It's my lucky die. Don't hurt it. And so you think, well, I really don't have to see the inside to know if it's weighted or not. Maybe I could just see what it shows me in a lot of rolls. And so you've got time to roll it 60 times, and you do that. And you tally up your results. And in the 60 rolls, let's say that you get 8 one spots, and you get the 2 spot 18 times, the 3 spot 11 times, the 4 spot 7 times, the 5 spot 9 times, and the 6 spot 7 times. And I would think immediately when you look at that, your eye is kind of drawn to the number of 2 spots. That seems like a lot. I mean, that is a lot of 2s. Because if the die is really fair, then each side would have a 1 in 6 chance of showing up. And so when you try 60 rolls, you would expect 60 times 1/6, 1/6 of the 60 rolls to show up with 2 spot. That's 10. So you're expecting 10 2s, give or take some for the chance error in the dice rolling process. But you got 18. That's a lot more than you expected. And the locals see this too. Their eyes are drawn to the 18. And they say, hey, let's do a little test of hypothesis here using our chapter 6 knowledge that we've just acquired. After all, there's a single proportion at issue here. It's P, the probability of getting 2 with the gambler's die. And so, like if you're the gambler, then your claim would be that P is 1/6 because you're claiming that your die is fair so that all the sides have a 1 in 6 chance of coming out. Whereas the locals suspect, based on what they saw in the data, that probability is not 1/6. In fact, they think it's probably more than 1/6 because they got 18 2s instead of 10. So you've got binomial test GC from previous sections, and all you have to do is use the summary data, say that you got 18 successes in 60 trials. The null thinks that the chance of success is supposed to be 1/6, and so you could do a quick little test of significance. And here's the basics out of the results you would get in the console. A 95% confidence interval for P runs from 18.8% to 43%. Every number inside that interval is bigger than 1/6. 1/6 is about 16.67%. And so the 1/6 is being ruled out as unreasonable based on the data just from the confidence interval. If you look at your two-sided p-value, it's about 0.89%. It's less than 1%. And so if the die, if the chance of 2s is 1/6, then there's a less than 1% chance of getting results as extreme as what we got here. So it's looking pretty bad for the null. Here's a little graph of the p-value to back that up. I mean, here's that little less than 1% chance, like what you got. So the locals, they're totally decided in their mind. Since the p-value was less than 0.05, they say, you should reject the null hypothesis. We conclude the die is weighted. Got pretty strong evidence of that. So we'll ride the gambler out of town on a rail or tar and feather him or whatever you used to do back in the wild, wild west. But you're cannier. You say, wait a minute. You folks decided to test on the number of twos because you just happened to see a lot of them, in that tally of the results. Your eyes weren't drawn to the threes or the fours or the fives because they weren't so different from the expected value of 10 that you would have if the die were fair. So what's so special, though, about the two spot? Is it really all that unlikely that at least one of the 6 faces would show a lot more or less than expected? There's 6 things there that can deviate from the expected 10. Is it really so unlikely that one of them would deviate so far from the 10? That seems more like the kind of question you should be asking. So we could try a little R code to simulate this for ourselves. So you don't have to be able to write this code yourself, but what this does basically is it simulates throwing a fair die 60 times and tallying up the results. So I'm going to copy this and head to RStudio like you should as well. And I'll make the screen a little bigger and paste it in and give it a try. And so this time, none of the 6 tallies departed that far from the expected 10, but just try it a few times. This one also not too much. This one not too much. But like this time, wow, we got 22 6s. That's really far from the expected 10. Let's try again. Nothing too bad here. But now we got 17 threes. That was almost as extreme as we saw with our 2s when the gambler's die was tried. Pretty close to what's expected there. Reasonably close. Reasonably close. Reasonably close. Reasonably close. And so, we've tried it a few times. And, most of the time we are fairly close to the 10s for all 6 faces. But a couple of times we got really far away on one of the faces. So it's I don't know. You can't really tell right now how unusual it would be to have a face that's 8 or more away like the 2s were. So I went ahead and programmed the computer to try that same process out 1,000,000 times. And each time to look at the face that was farthest away from the expected number of 10 and to record how far away it was. And more than 5% of the time, there was a face that was at least 8 away, 8 higher or 8 lower than the expected 10. So, that's a lot bigger than the less than 1% p-value the locals were getting. 5% is a lot bigger than 1%. And that's really not all. There's a lot of other patterns that you could notice in a die that would make you think, oh, it might be unfair. For example, if you had seen 13, 14, and 12, 1, 2, and 3 spots, and then 8, 6, 7, 4, 5, and 6 spots, then you might be like, hey, maybe this die is weighted towards the 1, 2, and the 3. See? So there's all kinds of like combinations of unusualness in how the tallies could show that you could notice and that would make you suspicious. What's the probability that a tally could catch your eye in at least some of those many, many, many ways? That's probably going to be a much higher than 5% probability. So that value from the binom test GC, that p-value that we got, is really much too low because it's answering a probability question that really isn't the right one. It's focusing in specifically on what we saw in our data rather than focusing on a question about unfairness in general. This practice of choosing a test of hypothesis based on a pattern that you notice in the data is called data snooping. And it will always usually result in these artificially small p-values. So what do you do about it? Well, to avoid data snooping, you have to decide on your test before you see the data. So that means you can't really test with binom test GC at all. Like you can't decide in advance, I'm going to test on how many 3s. Because, maybe the problem is the die is weighted towards 4s or 5s. How do you know in advance what to test on? Whatever you decide to test on, it needs to be on something even-handed that's not based on one particular fixed pattern, like a lot of 2s or a lot of 3s or something. So I suggest formulating an even-handed test of hypothesis like this. Null hypothesis, the die is fair. Alternative hypothesis, the die is biased in some way, but don't specify how it might be biased. And my idea for an actual test is this. First of all, let's figure out what cell counts the null hypothesis expects in each of the cells of the tally table. Number 1, number 2, each of those is a cell. And then we're going to find an even-handed test statistic to measure the difference between a tally table that the null expects to see, more or less, versus the table that's observed in the data. And based on that difference, compute a p-value. So first of all, let's work on the problem of what kind of table does the null hypothesis expect to see? Well, if it really is a fair die and you're doing 60 rolls, then you do expect to see 10 for each of the faces. 10, give or take a little bit, for chance variation in the rolling process. So you expect a table of all 10s. Now you're going to get some different table, most likely. You're most likely not going to have all 10s. You'll have some observed table that differs from it. But what you can do is that in each cell, you can take the observed number that you got in that cell, subtract off the expected 10, square that difference, because you don't really care if it's positive or negative. And so the squaring takes away the negatives. We're going to divide by the expected value. That's a kind of a scaling that this statistic uses. And that fraction, we're going to compute for every one of the cells. And then we'll add up those fractions. And the result is called a chi-square statistic, the Greek letter chi here. So if you were to compute it for the gambler's die data, You observed 8 ones, you're expecting 10 of them. Square that, divide by the expected 10. You observed 18 twos, you expected 10 of them if you're the believer in the null. Square that, divide by 10. And so on for the other 4 observed cell counts. And when you add up those fractions, you get about 8.8. So if you were using R like a calculator, you could type it in laboriously all in one line. So that's the test statistic that I'm suggesting. But now let's move to the idea of the p-value. I mean, is this test statistic, this 8.8, is it really a big number? Is it an unusually big number if the null is right? If the die is really fair, what are the chances of getting a chi-square statistic at least as big as the one we actually got? That's the p-value that seems more reasonable to try to compute. So if we were in class, we would actually give this a try ourselves. We could maybe pair up and have one of you roll a die 60 times while the other one watches and tallies up the results. And then you all get a calculator or use R and compute the chi-square statistic with your tally. And then just note whether your statistic was bigger than 8.8 or not. And then we could kind of compare all of us and have several of these chi-square statistics all done where a fair die was actually rolled. And the proportion of them that turned out bigger than 8.8 would be an estimate of the p-value. But we're not together. So why don't we just go ahead and get a lot of simulations kind of quickly using a little app here. So I'm going to open this in a new tab, and you kind of wait for a minute while it gets itself all set up. And this app can deal with many situations in the chi-square goodness of fit test that we're learning about in this section. But it's set up by default to deal with the gambler's die so that you don't have to enter any numbers here. But what you would do is, if you were using it for other situations, is you would enter the observed counts in your tally table here where I've selected and separated by commas. And if you're a believer in the null hypothesis that the die is fair, then you think that the chance of each of the different outcomes is the same. So 0.17, which is about 1/6, I'm putting that in, putting six of them in here, one for each face, separated by commas. So that's where you enter the null hypothesis view about the die being fair. And just to make my output a little bit nicer, I give names to the 6 different outcomes, 1 spot, 2 spot, so on. And what we see in this graph over here is a graph of what was observed in orange versus what was expected, which is all 10 in height. And so you can see those 2 spots standing out. And down here is a computation of the chi-square statistic. So like on the first row, you observe a 1, you expect a 10. 8 minus 10 squared divided by 10 turns out to be 0.40. That's the contribution to the chi-square statistic that comes from that first cell. 18 minus 10, square it, and divide by 10 turns out to be 6.4. That's the biggest contribution that's made for all the cells. You added up all these contributions, you get 8.8, the chi-square statistic. But what we can do with this app is we can make it roll a fair die 60 times using this information you've provided up here, and we'll get a new chi-square statistic. So we'll simulate. So this new bar graph, the orange still stands for what was observed. See these 18 twos. The gray still stands for what a null hypothesis believer would expect when you have a fair die. The blue stands for what we got in our 60 rolls of a fair die. The chi-square statistic turned out to be 5. I'm keeping track down here of whether the chi-square statistic exceeds 8.8 that we got with the gambler's die. This one did not. Let's simulate again. This time I got 0.8 for a chi-square statistic. This time I got 3.4. This time I got 5.2. This time I got 1.4. This time I got 4.6. So once we've seen this happen a few times, we could go ahead and simulate a lot. I'm going to go ahead and simulate like 10,000 times. Boom. It happens very fast. The very last simulation got me a chi-square statistic of 15.4, and you can see why that happened. It looks like I got a whole lot more 6s than expected. See here, this big blue tall bar, much higher than the 10. But what's most important is that I have now tried this 10,006 times, and 12.26% of the time I've gotten at least 8.8 for a chi-square statistic. So it's not all that unlikely to get an 8.8 or higher if the die is fair. That's what this app is teaching us now. I'll leave it for a minute and back to the slides. So that's the basic idea of how the chi-square statistic could be used to determine if the probabilities for the die to come up in various ways are the numbers specified by the gambler, 1/6 for each side. Let's look at another situation where we could apply the chi-square statistic to do some inference. Seating. So let's let P1 denote the proportion of all Georgetown College students that prefer to sit in the front. Let's let P2 denote the proportion of all GC students who prefer to sit in the middle of a classroom when they have a choice about where to sit. And let's let P3 be the proportion of all students who prefer to sit in the back. And, you know, in most of the classrooms in Georgetown College, there's one row that people think of as the front. And then there's usually 2 rows that they think of as the middle right behind it. And then there's a 4th row that they think of as the back. So that means that half the available space is middle, and 1/4 of the available space is front, and 1/4 the available space is the back. And I've got a little question here. Do the preferences of Georgetown College students regarding seating, do they match the space available? So what I mean is this. Is the probability that a Georgetown College student prefers the front, is it 0.5? And the probability that a person prefers the middle, is the probability that a person prefers the front, is it equal to 0.25? And the probability that a Georgetown College person prefers the middle equal to 0.5? And the probability that a Georgetown person prefers the back equal to 0.25. If that were the case, then student preferences would reflect available seats. Let's call that the null hypothesis. After all, it assigns specific values to these unknown parameters, just like the gambler was assigning specific values to the probability for each of the faces to come up when he claimed his die was fair. These probabilities are not all the same, like in the gambler case, but they are a specific assignment. We'll call it the null hypothesis. The alternative hypothesis is just going to disagree with us. It's going to say at least one of those proportions is wrong, so that student preferences don't really match available space. So In Math 111 survey, there is the variable seed that says where people in the survey were willing to sit. And when we tally, we find that 27 prefer the front, 32 prefer the middle, and 12 prefer the back. And so, that 27 looks like a lot more than 1/4 of the 71 students available. And the 12 seems like a lot less than 1/4 as well. So maybe does this data provide strong evidence that student seating preferences don't match available space? Let's check it out. So what you should do is go back to your app, and you want to enter these as your null probabilities and these values as your observed counts. And then enter some good names for the values, and then play with the app until you've got yourself a chi-square statistic and a p-value. So I'll just get you started here, but then you'll continue on your own. So let me get back to the app. You could go back in the slides to do that. Skip that. Let's see. Okay, here we go again. So the three probabilities were 0.25, 0.50, and 0.25. Make sure to separate them by commas. And the observed counts were 27 preferred the front, 32 preferred the middle, and 12 preferred the back. And how about we use front, comma, middle, comma, back as our names? And I seem to have, there's a comma, There we go. So what I'd like you to do is play with the app the same as before. Go ahead and do a lot of simulations and eventually get yourself a p-value, and you can decide for yourself about this situation. I'll give you a recap in the next set of slides.